All right, now I'm going back to my whiteboard, so hopefully you guys can see that. So we cover chapters 1, 2, and 3. Now we're just going to start 3 today, but so this week we'll be covering chapter 3, but then that'll give us a week to absorb chapter 3 and to do the homework. And then we'll do exam. We'll do the exam. So let's see how that goes. All right. But I want to just kind of stay on topic and get this covered. Chapters 1, 2, and 3. So there's going to be 3 problems. 1 per chapter. You're going to have 2 hours. So the exam is from 5:30, 7:30, 5:30 to 7:30. But it's the exam is only meant to be an hour and 15 minutes long, but I'm giving you 2 hours just because of technical difficulties and things like that with uploading. So it's virtual, right? So this is it's virtual, obviously. And so it's going to be in inside a Beachboard, Dropbox. So I'm going to put the exam in there, and I'm going to time it so that you have 2 hours to turn it in. I mean, you can turn it in late, but it's going to be marked off as late. All right, so you'll have the timer will say 2 hours to. So basically, the exam is 3 problems. This is the same exam style that I've given all my classes in the past that are face to face, and so it was meant to be taken in an hour and 15 minutes time frame. Most people are done way before that, but I always give everyone an hour and 15, and there was always 2 or 3 people that I wanted to take all that time just to make sure, so that was fine. But I'm giving you 2 hours because, again, technical difficulties, right? You have to take pictures of your exam or upload it to your computer. So make sure you got 2 weeks. You got 2 weeks to make sure you iron out all your, right? There was 1 homework assignment that you did. I just assigned today chapter 2 homework assignment. It's going to be due next week. You want to make sure you get all your technical difficulties ironed out. I think everyone turned in your exams. I was able to read your exams. There was just 2 people that I'm not sure if they were from this section or from the other section that had some technical difficulty. I couldn't see anything when I opened their exam. So you want to make sure that we iron that issue out, right? That you my recommendation is to basically just take a picture with your cell phone and then upload it. But if you want to do it like a completely e-version, then that's fine too. But I just got to be able to read it. I mean, if something happens, it happens, right? We'll deal with it. But I mean, just again, you got 2 hours to basically do your exam and then upload it. And that's it. Okay. Any questions on that? I'm sure you have questions on exam style, right? So obviously it's open notes, right? Because it's I posted tables. So tables are now on Beachboard, and let me just give you a quick snapshot of what that looks like. So, darn it, what the heck? What happened to my tables? All right. All right, so maybe I'll show you that later. I don't know where my tables ended up. But anyway, so the tables and appendices and the basically you're the appendix of the book. I posted on Beachport. So like if you're relying on the ebook, you can, of course, it's open notes, open book. Sorry. But I did post a table in case you don't have any of the books. There is an ebook. I know I've seen it. Everyone's been sharing it and the link and all that. But if you just want the tables, because chapter 3 we're going to need tables, then you can go download it from Beachport and just have the tables right next to you instead of going through your book, your ebook, or your physical book, and that kind of thing. Anyway, we'll talk more about that later as we get closer to the exam. Any other questions? You'll have to probably come off of mute if you guys have a question because I'm having, yeah. once I start lecturing, I really can't. I don't get. Well, unless if you at me, you can chat, and a little bubble pops up. But then everyone will see it because I'm sharing my desktop. But that's fine. All right, no questions?
I
Yeah.
have a quick question. In
Yeah.
order to prepare for your test, do you suggest we do some extra problems from the book, or your homework will be similar to your test questions?
So definitely do the homework.
Yeah.
To prepare. So let me say prepare. So you want to do the homework is number one, right? You want to review my example problems, right? And number three, so what I usually draw. So I draw from homework, kind of similar to the homework, and to example problems. So anything that's fair game right now is homework and example problems. Don't worry, I'm not going to ask you. I won't ask you to do the heat transfer of a spacecraft system. I won't throw something too weird at you that maybe I work on every day that is technically within the confines of chapters 1, 2, and 3. I'm basically going to draw from the book. So, and from not this book necessarily, I'm going to draw, but it's going to be similar type of homework problems that I'm going to draw from to create the exam. But in terms of creating, like you said, you had mentioned extra problems.
Mm-hmm.
Yeah, definitely. I mean, if you can go ahead and do extra problems, definitely I recommend that. That's going to help a lot. All right, because sometimes in the homeworks, I'm not for. Sometimes in chapter, maybe I don't know if in chapter 2 and chapter 3, in the solutions, when I post solutions, sometimes I post solutions to extra problems, so that in case you want to try those. I haven't posted the solutions. I'm going to do that tomorrow. I'm going to post the solutions for chapter 1. I was going to do that today, but didn't get around to it. Any other questions on the exam or anything before we start?
Yeah, so for the example problems, I was kind of looking at some in chapter 2.
Yeah.
And they seem kind of like a little basic. Are the YouTube lectures, like, do they have anything different, or are they similar to the in-class lectures?
Yeah, they're pretty similar. Well, that's good that they're basic. I mean, I am going to go over some example problems in chapter 2 right now. To me, they're not too basic, but
okay.
But I'm not going to get too much crazier than what you see on the example problem. I mean, obviously, examples. The first couple examples are very basic, right? They're just. But look at the examples later on, like 215. I'm going to go over right now. It's pretty involved. That's chapter 218. I'm sorry, 215, 216. Right, those will take you, if you're just looking at them for the first time, it might take you an hour to get those two done. Yeah.
Professor,
Thank you.
Yeah.
Do we have to sign in during the exam?
No. All you have to do is you mean to class? So what I am going to do, I'm going to open the lecture. Video, I guess. So I am going to have a lecture video at the time. Just at the beginning. In case there's questions, for questions. So in other words, I'm going to post the problem and then I'm going to hang around for like half an hour. So you don't have to join in. It's almost like an office hour, right? I'll be open in case someone is like, hey, professor, I don't know the equation for this and this and that, right? Or I don't know the density of water. So, I can go and just write it on the whiteboard, right? I can just say density of water equals 1,000 kilograms per meter cube, something like that. And I can leave that there. Or, oh, professor, I don't know this. I don't know the area of a cylinder, right? So I don't know right now. I haven't created the exam, but sometimes that pops up, right? And I haven't covered. I can't catch everything, right? So, and I shouldn't. You should know what the area of a cylinder is. Should I say that I did at your age there and at the heat of the exam, whenever, you know, pressure is on? Probably not. You know, I probably would have, like, I don't remember. So, you know, I can put that on the board here. So anyway, so we'll do the first 30 minutes. I'll have a lecture, but I won't be talking. I'll just say, if you guys have any questions, let me know, chime in. And then you can ask. And if you want to just leave it on just in case, that's fine. You can put yourself on mute and just, you know, hang out. But I'll do that. I'll open a lecture video at the beginning just to entertain any questions. So this is the first for me. I haven't done. Last semester towards the end, obviously we did the COVID-19 and so I had to do the exams. But what I was doing before, I was just sending the exams to the students, and then they had a whole day to turn them in. But I'm gonna just do this a little bit different this time. I'm gonna go ahead and just give you the 2 hours to do them. And so that means you have to download it, right? You have to open it. I'm hoping that that's enough for you. You know, there's not a lot of words, so it's maybe a 2 or 3 sentence problems and then maybe a little diagram. So then you'll have to just do that on your own, right? However you do your homework or your problems, right? You're gonna do it on the computer, or you're gonna do it on a piece of paper and then take a snapshot of that and upload it. That's totally up to you. But you know, it's an hour and 15 exam. It takes an hour and 15 minutes to do this. I'm giving you 2 hours, just so that for that technical difficulty part.
And the exam would be uploaded to Beachboard, and we'll just download it from there.
Yeah. So it all takes place within Beachboard Dropbox, right?
All right.
Just like homework, just exactly like homework, except you only have 2 hours.
Got it. Thank
It's
you.
a time. Yeah. Again, it's a timer. You still turn it in if it's late. I'm going to deduct, you know, a lot of points basically if you turn it in late. You know, I don't know how much, but it's going to be probably half off or something like that. But it's, you know, because 2 hours is more than enough, and this is just to prevent you from going and, you know, I don't know, doing whatever and going back 4 hours later. All right. So this is what I got to do to make it fair for everybody. All right. All right. Any other questions on the exam? We'll cover some more questions again next meeting. We will have a review on the lecture right before the exam. We'll reserve the last 15 minutes to do a review. Open it up for questions if you guys have any technical questions or anything like that, or the same kind of housekeeping questions, right? Okay, sounds good. I'm gonna go ahead and let's see what else we have on the list here. So let me go ahead and open up a new page here. All right. All right. So let's see, solutions. All right. So I'm posting solutions for homework number 1 after today's lecture. Maybe if not tonight, then tomorrow morning. So you can go over your homework and just compare, look at the solution, see what you did wrong. All right. Let's see. What else do we got to do? All right. So we are going to lecture right now. So I wanted to know if you guys are interested, but there is I think there is a career fair for CSULB. I think it's end of September. All right. So my wife she's a recruiter for Chevron. And she's been to Cal State Long Beach a lot of times. She was representing Chevron. And so I thought it would be a great idea to spend like 15 minutes talking about, you know, any questions, Q&A regarding how to prepare for this career fair, and what to, you know, because it comes up a lot. This is fall, and so you should be, if you've never had an internship before, then for those of you that are like sophomore, juniors, then you definitely want to attend this career fair. Now it's virtual, so there's a lot of things there. But she's already done like a bunch of virtual career fairs. So if there's any questions that you have, I'd like for her to come on for 15 minutes or so during our lecture, maybe towards the end of the lecture, and to entertain any questions that you guys might have. Sometimes there's questions on, you know, conduct during this lecture, during these, sometimes there's resume, and, you know, just things like that. So Is anyone interested? You guys interested to, if I can bring on my wife?
Yes, yes, sir.
Okay. Her name is Gabriela, and she goes by the same last name. Okay, so I'm gonna bring her on, and she'll do like a 15-minute Q&A to entertain any questions to get you ready for this career fair. Now, the industry is tight, right? The industry is shaky, I should say, right now, because of COVID. Due to COVID, right? Due to COVID-19. So she's in the oil industry, and oil industry is suffering right now because of no oil. Right? Basically, driving, right? No one's driving anymore. They're not driving as much. Driving's gone down, right? So their industry is really hurting, and they traditionally have hired many people, and they go to Long Beach every year and have many many permanent positions, many internships. This year for them, it's tough, but there's other places that are doing pretty good, right? So you might want to consider that, right? You think about that if you're targeting an industry that's kind of hard hit right now. I don't know what those would be. Anything that has to do with transportation is probably hard hit, or maybe not. Maybe certain delivery transportations are doing pretty good, but for sure the oil industry is suffering, restaurant industry. But like as an engineer, I'm not sure what the other industries are doing, like aerospace. So anyway, so you want to keep all that in mind, and you want to prepare accordingly, right? So there might be questions as to, well, just say you wanted to work for Chevron, because they're really good company. They have some of the highest starting salaries I've ever seen in my life, and they have really good pensions that are like the only people that compete with Chevron's pensions, or not pensions, I should say benefits, are government, and because Chevron does offer pensions. I don't know anyone else that offers pensions in terms of, but besides the government and states. So there might be some questions as to how do I prepare for a company, and I want to work for them, but this year is probably really bad for them. So do I go to grad school where I'm going to graduate now, or do I work somewhere else? Those kind of questions you can ask. All right, I'm going to go ahead. So we'll do that at the end of the next lecture, 15 minutes. I'm going to go ahead and start a new lecture page here. Good. All right. So where are we at? So hopefully you got a chance to go over my lecture notes my YouTube presentation that I gave. I know it's not the most energetic presentation in the world because I didn't give it to any students. I basically just did it on computer and posted it. But I'm hoping the majority of this chapter, we already covered a lot of this chapter, but there was some parts I didn't cover. For example, there was having to do with efficiencies I didn't cover. So I'm going to cover a little bit of that today. And then I didn't cover, so there was efficiencies of turbines and pumps and things like that you will need to look at that lecture. I'm not going to go too much into depth. Now there was, I did have one of you that did ask me sign convention. I want to do that really quick. I know I covered this. You could probably look at the last lecture. I know I covered sign convention. All right. So when we're doing energy analysis, it's very important how we determine what's positive and what's negative. So for example, I have a box, right? It's a tank. And inside the tank, I have heat, right? That's going to come in, and heat is going to come out. So the symbol for heat is Q. So heat is anything it's a form of energy that is dependent on temperature changes, right? So heat travels from hot to cold. So you basically would need to have something hot going to somewhere cold. If there's energy that's associated going from hot to cold, it's heat, right? And it's the symbol heat. So I'll just put here heat. Heat goes in and heat goes out. The heat that goes in, we always call that, this is the system here. And the control volume is this box here. This is our control volume, or control volume / surface, right? So we're only interested in what crosses the control volume. And for all the problems that we do from here on out for chapter up to chapter 5, we're only interested in basically, actually even beyond the whole class. We're only we draw a control volume, and then we're only interested in what crosses. So heat can cross, and work can cross, right? So work can come out, and work can go in. All right. So this is for a closed system. For a closed system, we're only worrying about heat going in and out and work going in and out. So anything when heat goes in, it's considered positive, right? You are heating a system, so it's by the perspective of the system. It's by the viewpoint of the system. See, the system's receiving heat, so it's a positive heat. The system's losing heat, so it's negative. It's very straightforward when it comes to heat. When it comes to work, it's the opposite, right? For work, it's the opposite. When work leaves the system, it's a good thing, actually. But so we call that positive. When when you need to put work into the system, that's a negative thing. So just if you can just memorize this is fine. Heat is very straightforward. Your system heat has heat coming in, that's positive. Heat leaves or you lose heat, it's a negative. So think of work as, usually we're going to be looking at piston systems, engines, pumps, power, right? That kind of like, for example, yeah, an electric motor. For an electric motor, you want to draw energy out of it, right? You want to basically you want to maximize your work out and minimize your work in. So therefore, getting work out of the system is positive. It's a positive thing. If our system requires work to put in, it's a negative thing, right? Because we're losing energy. If I need to crank that electric motor to get it to start, or a car, for example, you have to go in and crank it or do something, then I have to put work in. That's work that I'm not getting from the engine, so I have to put it in. So that's why it's negative. All right. So that's it on sign convention. Any questions? All right. Pretty straightforward. All right. Now, what I want to do is cover chapter 2, an example problem. So it's going to go ahead and create a new. So this is in your book if you want to follow along. This is in the recent book. So this is example 2-15 in your book. Okay, so it's power generation. All right, so let me read it right off of the book. Electric power is to be generated by installing a hydraulic turbine generator at a site 70 meters below the free surface of a large water reservoir that can supply water at a rate of 1,500 kilograms per second steadily. All right. So that was a mouthful. Let's go ahead and draw this situation, what's going on. So we have basically a reservoir, a dam in a sense. And goes like something like that. And we have an opening at the bottom there. Let's draw some water. So we have a fluid level there. This is that's the surface there. We're going to call that we're going to call a point here at the surface of the water 1, and then discharges water. Let's see. Actually, let's do this, and let's draw another surface of the water down here. Here's my symbol to designate surface of the water, and we're going to call it this point 2. All right. So what's happening is below the surface, there is some activity going on. Oh, all right. Let me give it a brown color here. Below the surface of the water, there's a turbine. See if I can go ahead and. This is a turbine. and water is coming out of that turbine. It's being pumped basically from the top. The water is coming from this reservoir at the top and it's coming down to the bottom. The height of this, let's see, is 70 meters according to this. $70 meters. And then what's driving that, what's driving this turbo pump is basically a generator. Actually, this is a turbine. It's not a pump. It's so what it's doing is water. Let me draw a streamline here. So water basically is coming down, entering this turbine here, and what's going is turning the blades of the turbine, and the generator is picking up the power. It's picking up and it's producing basically now electricity, right? So we're actually able to recoup electricity from the fact that we have all this high dynamic or this head from having this high water level, and we're charging it to a lower water level. So we're generating electricity. The flow rate, we know that this is m dot is equal to 1,500 kilograms per second. All right, so if the mechanical power output of the turbine is 80 kilowatts and the electric generator is 750 kilowatts, determine the efficiency of the combined turbo generator efficiency of this plant. All right, again, so if we're saying that the output is, let's see, what are we saying? Output of the turbine, so I'm going to say, so the output of this turbine, we're going to call, what's the best? Work of the turbine, the dot, is equal to 700, so equal to 800 800 kilowatts. In other words, that's how much we're getting out of this turbine. And then it says, and the electric generation is 70. So what's happening is we're getting electricity coming out here. So I'm going to say electric generation is equal to 750 kilowatts. So that's what we're recouping, basically. The generator, the turbo generator is producing 800, but then there's some losses, right? This is the work of the shaft, but there's some losses that go to the generator, some losses associated with generator. So there's a little bit less that we recoup in terms of electric power. This is electric. Right. So then we want to find what's the combined efficiency. What is combined efficiency? So I'm hoping that of turbo generator. All right, so I'm hoping that you got a chance to look at my video because I did talk about what is efficiency. So that's important here. All right, so what we want to do first, efficiency. What is, again, efficiency we designate with the symbol eta, basically. It's like, looks like an N with a tail. And the efficiency, usually the easiest way to remember efficiency is it's energy output, or in this case, energy rate output divided by what it costs you, what you're putting in, energy. Right. I hate when my pen does that. Oh. Hold on a second. It's the energy rate of what you're putting in. So it depends. It always depends on what you're looking at, right? It depends on the system. So the efficiency. So this is always going to be a number that's less. It's less than or equal to 1. If it's equal to 1, it's 100% efficient, and if it's typically less than that. So that's how we define efficiency. So what you need to do here is to determine the efficiency both We want to find the efficiency of the turbine. And we want to find the efficiency of the generator. That's the goal here. Okay, so let's go ahead and I'm going to need a new page. I'm going to go ahead and save this. Hopefully, let's call it 1.1 save. Okay, so we got to refer back to it. All right, so the again there was a cliff, and the water level was 70 meters. Basically from the high level of the water to the low level of the water. All right, so what we want to do is we want to look at all the energy associated with this, with the water system here. All right, so we're looking at EMEC, right? So basically mechanical energy. What is it? Well, there's potential energy, there's kinetic energy, and there's flow energy. The way we look at potential, we know we're going to say that we're going to take a measurement at, we're going to say at Z. The way we characterize this height, this is Z, right? This is the, so we know potential energy is equal to specific potential energy divided by mass is equal to gravity times Z, right? But if we say that, if we say Z1 is equal to 0 meters, then we can say Z2 is equal to 70 meters. Right. So our starting point is 0 meters. We're going to say this is where we zero our ruler, and then we go down and we measure 70 meters down. So therefore, the change in potential energy, which is what we're after, is equal to G times Z2. Right. And so let's see. Okay. All right. So which is equal to, it's basically anyway, we know what G is, and we know what Z is, Z2. Now in terms of kinetic energy, usually you look at the velocity divided by 2 squared of each point. There's 0.1 and there's velocity 0.2. Well, the velocity of 0.1 and 0.2, these are the surface of the water, and so though technically they are changing, this is a large reservoir, right? This is like the Hoover Dam, and so these levels aren't really changing; they're steady. And I think the problem said that this is a steady state problem, so this is steady. Therefore, your velocities are, velocity 1 is equal to velocity 2, which is equal to 0, right? These are your velocities of the water. This isn't the water going horizontally. This is basically the velocity going that way. The velocity of that surface going up and down. Those are essentially 0. So therefore, there is no kinetic energy. So therefore, there is no change in kinetic energy. So the change in kinetic energy is equal to 0. Now for flow, we look at pressure divided by the density at points 1 and 2. So because we're open to the atmosphere here, right? There's the atmosphere. So the pressure 1 and pressure 1 is equal to pressure 2, which is equal to P atmosphere. Therefore, the change of flow energy divided by density is equal to 0, because there is no change in, the only way you get flow energy is through a change in pressure. Now, obviously, in the turbine that was over here, right, there was, and then there's the generator like that. Obviously, there's flow going there. The velocity there is given, but we're not concerned basically with that. We're only concerned with 0.1 and 0.2. So relative to point 1 and point 2, the flow energy is 0. So therefore, the only thing going on here is that you have a change in potential equal to G times Z2. And so let's go ahead and write that down. So the change in potential energy is equal to G times Z2, which is equal to 9.81 meters per second squared times 70 meters. So this is going to give you the units. We want units of joules. This is going to give you the units of basically meters squared per second squared. So what we got to do is we got to multiply. We want kilojoules. So we know that 1 kilojoule per kilogram is equal to 1,000 meters squared per second squared. That's our conversion. Now in chapter 1 we did have a conversion, but the answer that we did, I think this was an example problem. Actually, it was in this chapter. In chapter 2 we did that wind turbine example problem. We reported the answer in joules, so we didn't have to convert, but because we're going to convert, we're talking, the answers are going to be, because what was given to us was in terms of kilowatts, right? We were given the output of the turbine, we were given the generation of the electricity at the generator. Those are in kilowatts, so we need to make sure our units are in kilojoules per second to give us kilowatts. So therefore, you have to be really careful here when you're working with units. So you're gonna have to divide by 1,000 to get kilojoules per kilogram here. And so it turns out that that is equal to 0.687 kilojoules per kilogram. All right, now that isn't the end of the story, right? We want to know, so this is the potential energy. In other words, this is how much potential energy that this state gives us, basically going from point 1 to point 2. So it has nothing to do with how much flow rate we have, right? This is just as we can generate 0.687 kilojoules per kilogram of energy by using the fact that the water is 70 meters different, right? Height difference. That's it. Now to give us the true total energy, we have to multiply by the mass flow rate. So for that, we say, let's look at the change in the mechanical, the rate, because we want the rate, we want an answer in terms of kilowatts. It's equal to, now we have to multiply by the mass flow rate times the basically little EMEC, right? Which is what we just calculated here. Which is equal to m dot, it's basically the change in potential energy. Therefore, we just calculated that. So we're getting that's 1,500 kilograms per second. And then we're multiplying by what we just found right here, 6.687 kilojoules per kilogram. Gives us a whopping 1,031 kilograms. Kilowatts. 1,031 kilowatts. So what I'm saying is that we were given the flow rate that comes out of here. And the flow rate that was given in the problem was right here. Was 1,500 kilograms per second. Therefore, we're going to get a whopping 1,031 kilowatts out of this, for that much flow rate, out of this flow here. All right. All right, now how does that match up with the efficiency of the turbine? Do you remember I told you the efficiency of the turbine is equal to, well, what we were told in the problem that there was 800 kilowatts at the turbine being generated. In other words, right here, this shaft is spinning, and I'm just going to say, hold on a second, this is kind of sloppy here. This is the work dot of the shaft. Right. So that's what this turbine is delivering to the generator. So this is the turbine, and this is the generator. So the turbine is delivering 800 kilowatts to the generator, but we have a total potential here. What's going into the turbine is the 1,031 kilowatts. In other words, this is how much. In other words, if we had 100% efficiency, we would get, instead of 800 kilowatts at the turbine, we'd get 1,031 kilowatts at the turbine. So what we took a hit. The turbine has basically it has less than 100% efficiency, right? So if we do that calculation, we get that this is 77.6% efficient for the turbine. Now for the, let me just draw a little division line here. The efficiency for the generator is equal to, we were given that the generator was producing 750 kilowatts, right? But we have the same input. The potential, in other words, if the generator was 100%, so if the turbine was 100%, it would transfer 1,031 kilowatts of shaft power to the generator, and if the generator was 100%, it would convert that 1,031 kilowatts of shaft power. It would convert it to 1,031 kilowatts of electricity. So therefore, the potential, the maximum potential that we can get of electricity is 1,031. Same thing, and therefore this is slightly higher or lower efficiency. This is 72.7% efficient. All right, so now you solve for the efficiency of the turbine, and you solve for the efficiency of the generator. Now to get the total efficiency, I'm going to write that here. Let's see if I can extend this so I don't have to create a new page. All right. The total efficiency, so that you don't think it's N turbine, is equal to the efficiency of the turbine times the efficiency of the generator, right? Which is equal to, and really we don't leave it in, we leave it in terms of decimals, so it'd be 0.776 times 0.727, and whatever that is. Let's see if I have the answer here. Let's see, I'll just have to calculate that real quick, if you don't mind, because it's not in the, it's not on my notes. So 0.776 times 0.727.
0.564.
Thank you. Equal to 0.564. All right, and this is the final answer. Right. That's the combined efficiency of the generator and the turbine. Now I'm not sure in your example book, I think they might have just asked you to just calculate the just the individual efficiencies of each system, of the turbine and the individual efficiency of the generator, but in my notes it said do the combined. So I did all three. Right.
What problem number was it again, Professor, on the text?
This is, so if you have the 9th edition, this is example. If you have the 9th edition, I'm looking at it right now. This is 2-15 on page, what is it, 83. Page 83. All right, so this, my notes when I created this was actually the 6th edition. This was actually example 2-16, but in this current book, it's 2-15. All right.
Professor, I have two questions really quick.
Yeah.
So the flow rate 0 because it's open to the atmosphere, right? So technically there's no flow rate. Energy, sorry, flow energy.
Yeah, because it's open to the atmosphere. We decided that we were looking only at, we're only considering 0.1 and 0.2 here.
Right. Okay.
Those are, we have to pick two states, and those are the two states. Yeah. So they're open to the atmosphere, so therefore there's no pressure difference. That's not what's creating the flow, right? The flow coming out of the side of the mountain is created by something else, right? It's not pressure. It's actually, it is a pressure here. So if we we measure the pressure there, obviously there's a huge pressure. And then so we would just be transferring pressure with potential, right? So at that point, there would be no potential energy between this red point and point 2, right? It would be completely pressure. But the other way to attack it is just look at the height, right? That's what's actually causing the flow, right? So it depends how you look at the problem, but this is the information. We weren't given this pressure here at the bottom. We weren't given that pressure, therefore we're going to solve this problem with what we were given. We were just given a height difference of water, so we solved it with potential.
Is there and then the last question: is there a way to know where was the energy lost in the system?
Good question. So energy loss, yeah, exactly. So we do have energy loss, right? The fact that these aren't 100%. Typically, energy loss is, especially in chapter 2. I'm just going to say, I'm not going to say forever, but say in chapter 2, is always in the form of heat. All right. So what happens is this this turbine is basically losing heat to the water, and this generator is probably, if it's inside the water, I don't think it is losing heat to its environment. I think actually the way the problem in the book, these aren't submerged. There's a side of a cliff does this, and then it goes down here like that. So they're kind of embedded into the cliff or into the concrete if this is the Hoover Dam. So they would be just transmitting heat to the environment. Heat, right?
Okay.
All right, good. So that's exactly it. It's dispelling heat, and actually in general, energy. Whenever we have engines and friction, and there's usually that transforms into heat. The final product is heat. Okay. Any other questions?
I have one question, Professor.
Yes.
Is this example a realistic values for efficiency of both a turbine and a generator? For example, the question was asking for the efficiency of the turbine and the combined efficiency of the turbine and the generator. So if we looked at just the generator was actually pretty efficient because out of the 800 kilowatts, it was giving 750.
Yeah.
So is that realistic in general, where generators are pretty efficient and turbines are not?
Yeah, exactly. They are. Yeah, it's true. It's generators are electric motors, and so they tend. Now these are none of these devices have anything to do with temperature change. In other words, they're not heat engines. We're going to talk about heat engines in chapters after chapter 6.
Okay.
Heat engines are the worst efficient type of energy conversion devices. Well, second to like solar panels, but these are just mechanical. They're only converting mechanical to mechanical. So the mechanical here is basically height, or what we call head, or pressure, and it's converting it to shaft work. So you're right. Generators tend to be very efficient, in upwards of about 90%, because they're converting mechanical to electrical, and the windings and everything like that are done to the point where you can easily get 90-something%. Turbines, they're trying to capture some of the pressure of the water, and so they're a lot less efficient.
Okay,
yeah.
Great.
Good
Thank you.
point though. Yeah, good point what you mentioned right now. It is converting. It's if you actually did the math, right, the energy that goes from the turbine, the electric generator can only really convert what's coming from the turbine, and that's 800 kilowatts. Of that, it's generating 750, so it's only losing 50 kilowatts of the total 800 going in. And then if you do the math, it's somewhere probably in the 90s.
Yeah, it's 93-point-something%.
Yeah, so that's very it's very typical for a generator.
Thanks, Professor.
Okay, you're welcome. So okay, so it's 5:30, it's 6:30. I want to just talk about one more problem. before we go. I was kind of hoping to start chapter 3, but that's going to have to wait probably till next. I might dabble in it a little bit. This is the beauty with virtual education, right? You're not going anywhere. I'm not going anywhere, right? You should have till 6:45, but anyway, we'll try to get through this real quick. So I do have to prepare for my next class. All right, so the last example is actually, I'm not going to cover it too much, but it's example in your book. It's actually the previous example, or is it the next example? No, it's the next example. So in the book, it's example. The next example was 216. Now, in the traditionally, I have done many exams where I give you a problem that's having to do with a generator, or the opposite of a generator is a motor, electric motor. So electric motors. And again, an electric motor backwards is called a generator. Right. So that's why I want to start this problem. So I give you some ammunition for the exam. All right. So let's suppose that you have an electric motor. This is actually a real, if you go out to the workforce, this is something they might ask you to do right away. This is kind of something that's given to engineers, for economizing, right? Like, what if we have a motor, for example, an electric motor in this case, and this, so basically this connects to the wall, and we get some work output, right? This is a 60 horsepower motor. So this is producing 60 horsepower. So this is something important that you understand. So the problem, I'll read the problem really quick. It says a 60 horsepower electric motor, and it has in parentheses a motor that delivers 60 horsepower of shaft at full load. So at full load, because if there was nothing attached to this and you connected it, it wouldn't be producing 60 horsepower, right? If this was just spinning in the wind, it would be producing nothing. It would basically maybe just overcoming some of its internal friction. So full load means that you're attaching something to it and you're turning it to its full capacity. If you have a knob here, for example, that is variable speed or something like that, you're turning it to its full capacity of 60 horsepower. That's with full load. And when they tell you this is a 60 horsepower motor, this is how much you're getting, right? You're going to get this. They're not telling you how much you have to deliver to the electricity. They don't never tell you how much. It's kind of in the boilerplate. It's kind of in the side of the box that tells you, well, how much energy does it cost me to get 60 horsepower? It's like our previous student right now that asked right now, are these really efficient? Typically they are. So it's going to be, if you convert 60 horsepower to electric power in terms of kilowatts, it's going to be pretty close. This is how much energy is going to come in that you need, but it's not 100%. So it's going to actually require more than 60 horsepower worth of electric power. So it's asking you right now, this particular motor is, let's see if I can just find, it's 89%. So this is the old motor. It's 89% efficient. You want to replace your company's looking at replacing it with a new one that is 92.3, yeah, 92.3, 93.2, sorry. And they want to say how much money is that going to save the company? Savings. And that's a very basic job. Your first assignment might be, if you work for a company, might be to see if it's worth is it worth spending the extra money that this device costs to swap it out with a new one? If it's getting old and it's 89% efficient, swap it out with a new one. How much are we going to save in terms of money, electric? How much electricity we save, and therefore that's money, right? So the problem states here that currently electricity is costing us, it's telling us that it's 8 cents. Your rate is 8 cents per kilowatt hour. Per kilowatt hour. That's how much electricity costs right now. And this is not really true. It's actually more than this right now. Today we're spending like 16 cents per kilowatt hour. And it depends, right? Last week when it was, or when was it that it was super hot? 3 days ago? 3 or 4 days ago, it was like 109 degrees or something like that. And Long Beach was crazy. So back then, electricity was more like 35 cents a kilowatt hour because everyone wanted it, right? It was at a premium, and so the electric companies will charge you more. So, so how much are we going to save? Well, it depends on how many hours. So we're looking at this per year. You're going to use this motor hours, right? 3,600 hours per year. That's how much we're going to use this motor. I don't know how many hours are in a year total, but it's not 3,600. It's something less than that. So, but you're going to just say your boss says, okay, we're going to run this motor about 3,600 hours per year. So how much do we save if we swap motors? So I did a price check on this today. I found a 60 horsepower. I went on to I went online, and I found that this motor today costs $2,360 for a new motor. I did this right before class, and it has a 3-year. This has nothing to do with the problem, but it has a 3-year warranty. Or 3-year guarantee that this thing's going to run, because if it within 3 years it breaks, you take it in, you get a new motor. All right. So all right. So anyway, I'll let you do the example problem, but basically what you do is you look at the to get how much you need to find out. Let me do this in red. You need to find out how much electricity is needed to get this 60 horsepower, given 89 or 93.2% efficiency. So you got to do this for the old, and you also got to do it for the new. So for example, for the old, the electric energy that goes in is basically equal to, it's 60 horsepower. Again, when someone says 60 horsepower, that's what you can expect here. You have to convert actually to kilowatts. To do that, it's I forgot what the conversion is. Damn it. I think it's right here somewhere. It's 700 and anyway. Yes, it's 0.74. It's 0.746 kilowatts per horsepower, right? And so this is equal to. Just gonna have to look at what is that equal to? So for the, I have to go change the page on my, sorry here.
44.7.
Thank you. Okay, it's 44.7 kilowatts. Can you do the new one? So actually, no, I'm sorry, this is the total. This is how much, sorry. For the old, we have to now divide by the, this is the shaft. So we need to divide by the efficiency of the old one, right? Can you divide this number by, which is equal to 0.89?
50.3.
50 point, how much? 50.3? Okay.
Yeah.
So it takes us 50.3 kilowatts of electricity to get 44.7 kilowatts of generation, right, at the generator, right here. Because 60 horsepower is 44.7. So it's taking us 53. So therefore, right, so that's how much, so we're losing some energy there. But then you look at what you end up doing is you look at the I'm sorry. How much electric work for the new one? And if you can do 44.7 divided by 0.932, Should be less.
47.9.
Thank you. So it takes us the electric motor for the new electric motor takes much less energy, right? It takes 47.9 kilowatts versus the old one, which takes 50.3. And so when you do the difference, can you do the difference for me? Save us some time here. It's about
2.3.
2.3 kilowatts.
Yeah.
Let's just say 2.3 kilowatts. Now, that's how much we're saving, right? This is how much we're saving by using the motor. But we want to know in terms of kilowatt hours, right? Over here. So what we do is we do 2.3. First, we multiply. You have to multiply by 3,600 hours. That'll give you how much total kilowatt hours. How much total kilowatt hours do we have?
8280.
8280?
Mm-hmm.
8280 kilowatt hour. And finally, we multiply by 8 cents per kilowatt hour, which now gives us, I'm going to do it in green because it's money.
662.4.
So this is how much money we're saving by changing that motor out. All right. 662.4. And thank you so much for the calculations.
Yeah.
So now you have to tell yourself, is that worth this $2,360? So basically you recoup your money in 4 years. It's like 4 years. I did the math earlier. So it takes 4 years to basically, it's $662. In order to get your money back, you have to run this motor for 4 years. But the warranty is only a 3-year warranty. So if this thing breaks within 3 years, or let's just say within 3 years is fine, but if it breaks before 4 years and you have to say 3.5 years, then you got to go buy a new motor, and actually it's going to be worse, right? So it's not worth it at this, but it has to do everything with this rate, right? I told you guys earlier that this is actually twice today. We paid twice this. So for twice this, then this thing, you can pay this thing off in 2 years, right? This 662 is actually twice that. It's actually at 16 cents per kilowatt hours, it's not going to be $662 that we save. It's twice that. So therefore, at today's rates, it's probably worth swapping it out. All right, so, okay, guys. Any questions? I know I held you out to the very end. All right, so I encourage you to check the recorded video in case some of this was too fast, or in case my chicken scratches were a little bit too hard to read.
Oh, they got a lot better.
Okay, it is.
Yeah.
All right, appreciate that. I'm working on it, but you know. All right, guys. So I was hoping to start chapter 3. Next meeting, we're going to do nothing but chapter 3. Hopefully, we'll get a lot of it done. All right.
Have a good evening, Professor.
All right, you too. I'm going to stick around, but I'm going to stop the recording here. I'm going to stick around though. If you guys have any questions, we're going to start office hours.
Have a good day, Professor.
All right, you too. All right, guys.
Thank you. Have a nice weekend.